Hi, my name is Johnny Vanderford with Lorain County Community College MEMS degree and Microelectronic Manufacturing Bachelor's degree, and Merit, the Manufacturing Electronics and Rework Institute for Training. I'm going to show you today something that we teach our students and train our workforce in here at the college, and that's how to make what's called a printed circuit board, how one is manufactured. I've got a printed circuit board in my hand that has a whole bunch of components. This is a relatively simple circuit board. You press the little button, and hey, the little lights come on and blink on each one of them right here. As a matter of fact, this whole board can actually be manufactured in high volumes in a little bit less than 1 minute per board. And I'm going to walk you through the overall process of the machines and materials and equipment that it takes to actually manufacture one of these boards. And we want you to know that everything that we're about to talk about, we actually teach in our associate's degrees of MEMS, which trains on a little bit more of the hands-on technician level work, as well as our Bachelor's of Applied Science in Microelectronic Manufacturing that trains on more of the operator level, operator for the equipment, programming and engineering. To start with, we actually start with a bare circuit board here. So this is a circuit board that has no components attached to it at all, which is how generally most circuit boards start out with, is without anything there. And essentially manufacturing is kind of done in a 5-machine process. We're going to start with machine 1 and work our way down. The first process that we actually teach in is this machine here, which is called a stencil printer. This one is made by Panasonic, which a lot of our company supporters actually have. This is similar to stencil printing for like a t-shirt, for instance. We use this big frame here called a stencil, which, if you were to look very carefully, has a whole bunch of holes in it. Thank you, John. And those holes actually align up with some of the holes that are on this circuit board as well. And if I were to put this, in, let me see if I can do this correctly here, do it quickly. Oh my gosh, I'll put the circuit board underneath it. And okay, it's taken me a little bit of some time, as it probably should here. Where have I got it? Oh, there's the pads. You see that? All of the pads align up inside of the holes. And I look pretty silly doing it, which took me about, 10, 15 seconds, 20 seconds to be able to do. And it's probably not very accurate if I do it by hand. But that's why we use this machine. On the inside of this machine, we have a vision recognition system that looks for small markers on the stencil right here called fiducials. These small holes that are in the corners are alignment marks that it's going to align this stencil up with the same alignment marks that are on the circuit board. So what I'm going to do is I'm going to push this stencil into the machine, push it all the way back, close this up, and then by hitting the run operation, it pushes the stencil forward, and a camera underneath the stencil comes in, and in less than a second, both fiducial marks are recognized, aligned up, and ready for this stencil to be used for a printing process called solder paste printing, is what this is. Now the actual solder paste, what that looks like for this particular machine, let me just get this prepared to be able to do this here. There we go. Thank you, John. So solder paste is soldering. It overall is a process in which metal, which melts at a low melting point, is heated up, melted, and then connects both electrically and mechanically printed circuit board components down to the board and to the actual printed circuit board component. This stuff that I'm holding in my hand, which kind of looks like gray peanut butter, it's got about the same consistency as peanut butter does. See that? This is actually made of lots and lots of thousands and thousands of small, tiny metal particles, which are made out of tin, copper, and silver, and then sometimes lead for military purposes. On the screen that I've got over here, I've actually got a close-up image of what this looks like after it's been printed down onto the pads. These gold images here are the actual pads, and these small little spheres, what we would call particles, are actually pieces of metal that connect up to or that will eventually be used to connect a component down to the circuit board electrically and mechanically. But we have to have this solder paste actually put down on top of our circuit board. And here's how we're going to do that. I'm going to take this solder paste and quite literally slather on the lather, so to speak. This is like making the world's worst tasting peanut butter sandwich, folks, is what that is. There we go. So we've got some solder paste on there, and obviously that's pretty messy, what that looks like. But fear not, what we're going to do is tell the machine, yeah, we've actually put that in the front of the machine, and it's going to bring those two blades forward. Those are what we call squeegee blades. Those two squeegee blades that are on the inside are going to be used to push the solder paste on a circuit board, which is going to be fed by a conveyor that is located over here on the left-hand side. The circuit board is going to go into this conveyor and be fed into this machine, put underneath one. I've actually already got one in there right now. So let's actually push, let's actually get this part started here. So we've got one loaded. We're going to recognize it. So it's going to align up the fiducials, the registration marks, on the circuit board to the mask. And in less than a second, it's all aligned up underneath it. We're going to begin a printing process. Now, normally speaking, the printing process is only done once. But look at how I smeared that paste down on the stencil. I'm going to come down with that squeegee and smooth that paste out. As it prints it, it's going to fill the open holes of that circuit board that's on there. And as it's doing this, you can see it's starting to smooth out the overall print of that roll. It's starting to look a little bit more. It's getting the air pockets out. It's getting some of the materials out. This process is considered to be somewhat of a critical process because the alignment of so many thousands and thousands of small parts that it takes to actually make a circuit board all starts with how this machine, a stencil printer, aligns up and prints the paste evenly across all the holes. So now that it's done printing, it's printed 4 times, we're going to unload the circuit board out through the front. Normally it's going to come out through a conveyor system because this is a high volume production machine. We're going to take this out, and you can see that our shiny pads are now covered with a dull gray-like material. And there's thousands of small circuit board pads on here that we've got to make sure get connected up correctly that to our circuit board elements to come in the next set of processes. All right? So the next thing that we're going to do, the second machine of 5 in the manufacturing process that we teach, is how this circuit board gets inspected. Now obviously I can't look at all the thousands and thousands of circuit board pads that are on here to determine if they're any good. I need a machine to help me out with that, and that's actually going to be done on this machine right here. I'm going to place the circuit board down on this conveyor system, and I'm going to tell this machine right here, this is what we call a stencil print inspection system. I'm going to turn this on, and now this guy is ready to go. Manually this comes in, and this is now taking 3-dimensional images of all of the pads as it goes down through this circuit board to determine if the correct amount of paste has been applied. This says, oh, a continuous no good is occurring. We sort of programmed this in advance with it here to be able to show something like that. It says, okay, one of these pads doesn't have the right amount of solder paste on it. Just one. Look how many thousands there are in here. Here, all of those are pads. Here, all of these are pads. And we can look at all these as well. We take a look at a 3-dimensional image of a pad, and this says, the correct amount of solder paste has been applied. All of them are green and within passing specifications. Except for this one. Except for this one right here, it says, wait a minute, whoa, 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 whoa. This one doesn't have the right amount of paste that's been applied to it, right? So what can we do? We could risk processing this whole board if we wanted to, or if I was a manufacturer, I'd spend a minute or two cleaning this circuit board up and see if I can fix my printing process, because this step of stencil print inspection is so critical that future steps, once I start putting all the components down on top of this, I really do run a risk of having worse problems occurring later on once this is here. For the purposes of the demonstration, I'm going to allow this part to pass. All right? So this is now going to come out on the other side here. this circuit board is now ready for the third machine, which is this machine right here. This machine is what we call a pick and place system. In a nutshell, this machine is the world's fastest carnival claw game. It takes circuit board components, which come on something called tape and reel. See one of these guys here? And if one were to look carefully at one of these tape and reels, one would see that there is lots and lots of small circuit board components. All of the circuit board components on modern day high volume manufacturing equipment come in on tape and reel. From the large components such as this chip, which is going to be put down to our board, to the very small components which are so small I actually have a hard time seeing them with the naked eye, right? Electronics kind of all follows one particular trend, in that our next microelectronic product, or our next consumer electronic product, I want more functionality inside of a lower cost, more effective, and easy to produce product that will last a long time, right? That's what we all want on our next cell phone, so I have to cram more and more functionality down into smaller and smaller parts. And that's what this machine is really good at doing. This machine is going to grab components from these what are called feeders using two different heads and put them down on the circuit board. All 108 of them. So let's start at warming up first. You can see that there are two heads on the inside. One in the front that has 16 pickup tools, and one in the back that has 3. The one in the front is used for picking up very, very small parts, and the head that's in the back is used for picking up very, very large parts. And so right now, what's occurring is that it's origining itself so that it can figure out where it's located at. John, I'm gonna push the board in. The board is now being fed into the machine, and it's now sitting in a place that's ready to have parts placed on top of it. First thing it's going to do is align up to the same fiducials that both the prior two machines have been programmed into it as well. Right now, it's using a red light to scan in to see where's the first of those fiducials. This thing is able to place down to kind of the sub-millimeter levels of accuracy. So, what's actually happening right now is that it's making sure that it's in the right spot. Now check this out. Next, right now what it's doing, it's picking up components. It picks up about 16 components up in the front, places down 16 components. Then, do-si-dos with the machine that's in the back, and places down approximately a couple of components there. Oh, it says it's got a little bit of an error. Hang on one second. It says it had a hard time picking something up. Yep, there we go. So now we're going to come back. It's going to come pick up a couple more parts. The front one's picking up parts as fast as possible, and do-si-doing with the machine that's in the back, which picks up much, much larger parts. These two heads work in conjunction to put up approximately 8 parts per second. We teach students how to program this machine, as well as how to pick up, as well as how to troubleshoot parts of this machine. The board is now completed. These parts have been physically placed in the correct area of the circuit board. You see that? And there's lots and lots of small components that get put down onto this circuit board. At the top speed, this thing can place approximately 8 parts per second. We just ran ours at approximately 5.6 parts per second is where we have ours running. The fourth machine that's on here is this large oven, which I'm going to press the button and send this guy on into the next machine. I think so. Come on. Maybe not. Oh, is there a board on the other side, John? No? Well, we'll just have it. We'll mosey him along right there. Thank you very much. There he's put on there. This is what we call a reflow oven. In a nutshell, this oven is a big pizza oven that heats up hotter and hotter along the way. All the way until about right here, those little metal spheres that are inside the solder melt and connect down to the circuit board and up to the parts across the entire board, and then eventually it cools down and out onto the other side of it, and we get a circuit board which looks like this, where all the parts are electrically connected, physically connected, and ready to be tested for functionality. This process right here takes approximately 8 minutes to do for the overall thing, but in the meantime, the other machines can produce one board every single minute. Let's move on to a couple more steps of the process here. So, all right, the fifth machine, automatic optical inspection. Here I've got a circuit board that has a little bit over a few hundred components, but some of these components are incorrect. I've got one that's sticking up in the air like this. I knocked one of the very little ones up off the top. I've put one of these battery clips on with the wrong polarity and globbed down an extra large amount of solder onto one of these bottom chips. What I do with this machine is I feed it into a small conveyor on the left-hand side and a three-dimensional imaging system on the inside of this that uses RGB LEDs and moire lines is now quickly scanning through this board. And every single time it scans any defect that I've programmed into it, it says, this one right here, you've got too much solder on top of these leads. And it's located on this part of the screen here. It's going to continue scanning. This is the progress block. It scans, it says, aha, I found a battery clip that has lifted up. I found a battery clip that is the incorrect polarity. It says wrong polarity. And finally, what it should find, if I've programmed this correctly here, if our students have programmed this correctly here, we've got the right program in, one of these smaller components up on the top should actually be bad. There it is. It's found it. It says there's something missing here. Either it's the wrong component or it's missing. This board now is ready to be fixed. Now this is a visual inspection system, an automatic visual inspection system. I can use this machine to look at the chips, but sometimes I have a chip that is a little bit more complex. So sometimes when we're manufacturing circuit boards, we have very, very large components that have lots and lots of connections underneath it, such as this Wi-Fi card. This central processing unit, the CPU, has about 484 different pin connections underneath it that are all soldered down to the printed circuit board. Unfortunately, I can't see either of them. The bottom of it has a whole bunch of circuit components, and the bottom of this chip is actually what I want to look at to make sure that the chip has been manufactured correctly. The only way to inspect this chip is to use our X-ray microscope by Creative Electron. I'm going to turn on, I have one of these on the inside of the machine, so I'm going to turn this on, and it's focused at the center of one of these chips. Now as this machine starts to warm up, this machine shoots X-rays down through the chip and produces an image very similar to what a hospital would see as an X-ray system, but actually kind of inverse. All of the black ball components that you are looking at here are all components that are underneath the chip. They are solder joints. A solder joint underneath the chip should look like a dark ball. We look for things where the solder joints are bridged together, where there's a bridge that could, or a grayish, whitish look to it, which would indicate that there is a gap. In addition to that, we can see other chip components that are underneath the circuit board, as well as the lines that are on the inside of the actual chip package itself. Some of the things that we look for, one of the things that actually occurred fairly recently with our inspections, was looking at a ball grid array chip. This is a RAM chip, and if you look, there's all kinds of little white dots that are mixed on the inside of the solder joint, darker black dots. Those white dots are air pocket voids that are caused by processing this solder incorrectly, be it either from cooling it down too quickly or by using expired materials. In the case of something like this, if that was found on the underneath of this chip, what we would have to do is repair the chip using a machine called a ball grid array rework system, a BGA rework system, which is another thing that we train on. Let's head on over to the machine. There we go. So what you're looking at with this machine here is a BGA rework system. What this machine does is we load a circuit board up that, for instance, this one right here has had a chip actually removed from it. So there is a large, you can actually see if you look very carefully, there's a large number of pin connections that are underneath that chip, all right? And additionally to that, I'm going to slide the circuit board in here. In addition to that, I've got a chip right here that has been removed so that I can put it back on. And underneath the chip, you can find that there are hundreds and hundreds of pin connections underneath it. What this machine does is something that most human operators really cannot do, and that is to align up a large number of connections on a ball grid array chip to a circuit board, and that is done using a camera imaging system. There are two images that are being displayed on top of one another. This camera is looking up at the chip and down at the circuit board. Here, you are looking at the actual circuit board itself. I can move the circuit board around to put the whole circuit board on screen. Now I'm going to kind of lock this into play now. There we go. Now the other side, I'm going to turn the circuit board image down and turn up this more bluish looking image here. These blue images right there are the actual chip. By rotating some knobs here, I can actually cause this whole chip to rotate like that. See? I'm going to zoom in a little bit careful so you can see kind of what the center part looks like. And you can see that by rotating this, I can actually cause the chip to be go into the right spot. By moving a couple of other knobs, I can actually move the board in X and Y coordinates so that it aligns up to the blue balls on top of the chip. See that there? Kind of zooming out, we can see that in general, there might be some additional alignment that has to be done, but an operator, what they would have to do is align up the entire chip, and then this process that occurs afterwards with the camera, this chip comes down on top of the circuit board, and then the whole circuit board and the chip begin to heat up by blowing hot air from both the bottom and on the top of this, which causes the solder to reflow and remelt, and eventually this machine lets go of the chip and would connect it up to the circuit board. Not quite with that gap with it on there, but that's just more for demonstration purposes. That has to be done if the chip has been manufactured incorrectly or with defects that we've seen in either the automated optical inspection system or the X-ray microscope. So yeah, that's the overall process of how you go from a bare board to a functional circuit board. If you want to find out any more, head over to Lorain County Community College website and look up MEMS, or Microelectronic Manufacturing, or MERIT, Manufacturing Electronics and Rework Institute for training. Thanks very much, folks. We'll see you later. Bye-bye.